Hello everyone, welcome back to yet another class for mathematics. Today we'll be doing implicit differentiation, which is the second part of this chapter. Okay, so before we get started, if you guys have anything you want to ask from the first part of differentiation, the class we were doing last, send me any questions you may have. You can send it through WhatsApp. Then I shall discuss them on stream. Otherwise, we'll get started. Okay, so go here, make my pointer bigger. Okay, doke. Okay, so for all the equations you've seen so far, it's always y as a singular function of x. For example, y as a function of x, maybe something like 2x squared plus 1, or 2x squared plus ex, something like that. And then usually they'll ask you to differentiate it, right? And then you just differentiate normally. However, there are certain equations that do not look like that. For example, the equation of a circle, x squared plus y squared equals to 4. If I ask you to find the gradient dy dx of this curve, what are you going to get? Well, it depends, right? Because now your gradient depends on two things. It depends on the y coordinate and it depends on the x coordinate, because if you draw a circle out, and let's say we compare that with a regular quadratic, so for a quadratic, the gradient dy dx only depends on the x coordinate. So if I say x is here, I'll get this gradient. If my x is over here, I'll get this gradient, right? However, for the circle, if I say I'm going to pick this x coordinate, I actually have 2 points. It could be this one, it could be this one, and the gradient of the tangents of those points are different. So your gradient actually depends on both x and y. But this one only depends on x. So for situations like these, you have to use implicit differentiation. So how do you use implicit differentiation? Well, let me show you. Get rid of all of that. So you're trying to find dy dx, right? So the first thing you want to do is differentiate both sides with respect to x. So you just go d dx bracket x squared plus y squared equals to d dx 4. So when you differentiate one side of the equation, you also have to differentiate the other side of the equation. It's a bit like adding something or multiplying something. You add something on the left side, you must add something on the right side. Okay, so when you differentiate two separate terms like this, you can differentiate each term separately. So you're essentially doing differentiate x squared plus differentiate with respect to x y squared. And if you differentiate a constant, in this case you're differentiating 4, you just get 0. Okay, now differentiating x squared with respect to x, that one is easy enough. We know how to do that. That's just 2x. However, you're trying to differentiate y squared, but the problem is you're differentiating with respect to x. Oh no, you can't do that because this is y, this is x. So what should you do? Well, what you can do is you multiply this thing by 1, and instead of writing 1, you would write dy over dy. You're kind of abusing the chain rule here, okay? And then you can see that d and dy, we can just swap them around, which is going to give us dy dx and then d dy y squared. Because when it comes to multiplication, the order doesn't matter. So now you can see here, we have d dy y squared. So you're differentiating with respect to y squared. So we can do this, which means we are going to get what do we get? We get 2y. And we are trying to find the gradient, which is dy dx. So now we just make dy dx the subject. So dy dx is going to be equals to negative 2x over 2y, which is negative x over y. And we're done. That's it. Let's say you want to express everything in terms of x. You can actually do that by making y the subject here. So y is going to be equals to 4 minus x squared, and then you square root. So you get plus minus, which means this would actually give you negative x over plus minus square root of 4 minus x squared. So what does this tell you? This tells you that suppose I were to draw a circle, and then I want to find the gradient when x is equals to 2. And my y is equals to whatever x is when, hang on, let me just draw it like that. So when x is equals to 2, what is my y going to be? Well, let's put it into the equation. We have 2 plus y squared equals to 4, so y squared must be equals to, oh wait, that would just be 0, wouldn't it? Let's not choose 2, let's choose 1 squared. So let's say we have a circle, the radius of the circle is 2, so let's say we pick 1. So y squared is going to be 4 minus 1, which is 3. So y is equals to plus minus 3, root 3, sorry. So this guy here is going to be y equals to plus root 3. And this guy here is going to be y equals to a negative root 3. So the coordinates at these 2 points would be, 2 root 3, and then this one would be 2 negative root 3. So if I want to find the gradient at, let's say this is point A, this is point B. So the gradient at A is going to be equals to negative x over y. X is negative 2 over root 3. So my gradient would be negative, which makes sense because if you were to draw the tangent, you would get a straight line with a negative gradient. However, if I want to find the gradient at B, I would put in negative 2 over negative root 3, which gives us 2 over root 3, and you can see this is a positive number. So if I were to draw a tangent over here, the gradient of the tangent would be positive, which is what we expect to get. So that is implicit differentiation. Okay, so that is the simplest example. Let's try a different example. Moving on. So example number 2. Let's say we have x squared plus 2xy plus y squared equals to 20. And I want to find dy dx. Okay, so first things first, we're going to differentiate both sides with respect to x. You know what? Let's just make this a bit more interesting by putting an x over here, just because we can. Okay, so we're going to start by differentiating the left side. Let me do it like that. Okay, so if I differentiate this guy here, I'm gonna get, and you know what, I'll just write it out one by one, just to show you every single step. So d dx 2xy plus d dx y squared. So this guy is gonna give me 20. So if I differentiate x squared, I'm gonna get 2x. If I differentiate y squared, I'm gonna get dy dx and then 2y, right? Similar to what we were just doing over here. Okay, what about the guy in the middle? Well, you can see the 2 is actually a constant. We can take the 2 out. So that would be 2 d dx xy plus something like that. So how can we simplify this? Well, you can see here we actually have a product x times y. So when you have the product, you have to use the product rule. So remember the product rule? We did that in the last class. So d dx xy is actually going to give us u, and then we differentiate v plus v, and then we differentiate u. Okay, so we can't differentiate y because this is with respect to x, so we have to introduce dy and dy, and then we swap the top parts, so x and then d dx dy dy and then y. This one we can, if we differentiate x, we just get 1. And now we're gonna swap the numerators. So now we have x and then dy dx d dy y plus y. So differentiating y is going to give me 1. So we have x dy dx plus y. And done. So that's how you differentiate xy. Okay, let me just move that over here. And let me move these out of the way. Okay, so we are going to end up with 2x plus 2x dy dx plus y plus dy dx 2y equals 20. You're essentially treating dy dx as a term on its own, okay? So what we are trying to do is we're trying to find dy dx. So we need to put all the dy dx's on one side so that we can factorize it out and then move everything else to the other side. Okay, so here we go. We're going to expand this guy first. We have 2x plus 2x dy dx plus 2y plus dy dx 2y equals 20. Then we're going to factorize the dy dx's. So we have 2x plus 2y, and the rest we'll chuck it on the right side. So 20 minus 2y minus 2x. Therefore, dy dx must be 20 minus 2y minus 2x over 2x plus 2y. Divide everything by 2, we get 10 minus y minus x over x plus y. And that is how you find dy dx. Okay? There you go. Finished. If you want to express everything in terms of x, you can actually do that. You have to start with your original equation and try to find y in terms of x. So let's say we attempt to do that. You can see on the left side is actually x plus y squared, right? Equals 20x. So x plus y equals to square root of 20x with a plus minus, and then y is equals to negative x plus minus square root of 20x. So now that we have y in terms of x, we can chuck that in here. This is not going to be possible for some equations, but some equations you can do that. It kind of depends on the question, really. So you chuck that in here, you get 10 minus x, so minus 2x, plus minus square root of 20x divided by x minus x, so we get plus minus square root of 20x. And that is your gradient in terms of x only. There we go. Done. Okay. Right. Let's go and do one more example. Well, we're going to do a couple more examples, actually, not just one more. We're going to do one more. That has to do with the quotient rule. So let's say we have do they usually introduce a quotient rule? Quotient rule is kind of rare though. Let me see if I can find an example from the textbook. Yeah, come to think of it, I don't think they would actually ask you to use the quotient rule for this one. However, I wouldn't put it past them. I'm going to come up with a random example. Let me think. Nah. I don't think you would ever want to use the quotient rule actually, because any kind of quotient you can always just multiply everything by the denominator to get rid of the denominator, and then you end up with the product rule. So you can always use just the product rule. You don't have to use the quotient rule. Okay, anyway, let me show you one other weird example. Let's say you have y equals to x to the power of x. And then the question is, find dy dx. Oh, so this is actually nothing like what you've done before, right? You haven't actually done differentiation like this. However, you can actually solve this because all you need is implicit differentiation. But first, you need to take logs on both sides. So you're going to get ln y equals to x ln x, okay? And now you want to differentiate both sides with respect to x. So on the left, you can't differentiate ln y with respect to x, so you have to introduce the dy dy like so. And then on the right, you can see it is a product, so you just use the product rule. So you start by writing x, differentiate ln x, you get 1 over x, plus ln x, and then you differentiate x, which gives you 1. So simplifying this guy on the left, we get 1 over y equals to 1 plus ln x, and therefore dy dx must be equals to y times 1 plus ln x. And as you can see, y is actually x to the power of x. And therefore, that's how you find the derivative for x to the power of x. There you go. Okay. What else can we do? All right. You know what? Let's do some parsing questions. Okay, let's do this one. Question 3. There's actually not that many questions in the past year papers. There's only 20 for this one. Okay, so you're given this equation and you want to find the derivative. So what you want to do here is you can try to expand it. So you will get x cubed plus 3yx squared minus y cubed equals to 3. And then you differentiate both sides with respect to x. So this gives you 3x squared. This guy in the middle, you have to use the product rule. So y, and then differentiate x squared gives you 2x. And then x squared differentiate y gives you dy dx. And then minus 3y squared. Okay, so simplifying this, we get 6yx plus x squared dy dx minus 3y squared equals 0. So I'm going to make dy dx a subject, so we throw everything to the other side. But 3y squared minus 3x squared minus 6yx. And then dy dx is therefore 3y squared minus 3x squared minus 6yx divided by x squared. Wait a minute. Why is it different? Did I mess something up? Hang on, let me see. Y, and then differentiate this, we get 2x, yep. Plus x squared, differentiate y, we get dy dx, yep. Oh, I forgot to put a dy dx here. Yeah. Hang on a second. I messed up this one. This one should have been dy dx, y 3y squared. Yep. So we're gonna have to factorize the dy dx from the terms with dy dx. That is x squared minus 3y squared. And the rest we're gonna trade on to the other side, which gives me negative 6yx minus 3x squared. So dy dx must be equals to 6yx plus 3x squared over 3y squared minus x squared. Oh wait, there should be a 3 here. 3 right there, so 3 here. Then we divide everything by 3, we get 2yx plus x squared over y squared minus x squared. And done. Part 2. Hence, find the exact coordinates of the 2 points on the curve at which the gradient of the normal is 1. Okay, so we're trying to find 2 points on the curve at which the gradient of the normal is 1. Right, so we know that the gradient of the tangent is dy dx. So the gradient of the normal is going to be negative 1, the gradient of the tangent. Right, it's the negative reciprocal. So that's going to give us x squared minus y squared over 2yx plus x squared. So that's the gradient of the normal. Okay, and it says find the points where the gradient of the normal is 1. So equate that to 1. So we have 2yx plus x squared equals to x squared minus y squared. The x squareds cancel, and then we have y squared plus 2yx equals to 0. We can factorize the y out, so we have y plus 2x. So either y is 0 or y equals to negative 2x. So when y is 0, what is x going to be? Well, x is going to be cube root of 3. And then when y is negative 2x, let's chuck that into our equation here. So negative 5x cubed plus 8x cubed gives us 3x cubed. So x is equals to 1. So when x is equals to 1, y must be equals to minus 2. Therefore, the two coordinates are cube root of 3, 0, and 1 minus 2. There you go. Okay. Yeah, that's it. That's it for implicit differentiation. So all that's left for you to do now is to attempt exercise 4D. Excuse me. And you can try the past years. Let me just check textbook. Yep. So next class, we're going to do parametric equation. And I'm going to show you how to differentiate the inverse trigonometric function. Right, so for today, all you got to do is try 4D and the past year papers, which is only 20 questions. That's not many. So try those and see if this is okay. This is not something you've done in AdMath, so I suspect you guys might find it a bit tricky. So feel free to ask me any questions if you are having any difficulties. But yeah, I think we shall stop here for today. Well, actually, we have quite a bit of time left. Should we just continue? We could just continue. You know what? Maybe we'll just continue. Maybe I'll show you how to differentiate the inverse trigonometric functions as well. You know what? Why not? Let's do that. All right. Let's do this. Let's say we have y is equals to arctangent x. So arctangent x, let me just do it like this. Okay. Sometimes arctangent x is also written as tangent minus 1x. So tangent minus 1x does not mean 1 over tangent x. It does not mean tangent x to the power of minus 1. I mean, you can also interpret it as tangent x to the power of minus 1, but in the context of A levels, when you see tangent to the power of minus 1, it actually refers to the arctangent, the inverse function of tangent, not tangent to the power of minus 1. Okay? But just to make it less confusing, I'm just going to stick with using arctangent here. So there is no ambiguity. So if I give you y equals arctangent x, and I want you to find the derivative of arctangent x, what should you do? Well, first things first, we don't know how to differentiate arctangent because that is not one of the basic derivatives that we can differentiate, right? However, we can move arctangent over to the other side, which is going to give us tangent y equals to x. Cool. Now we're going to employ what we've just learned, implicit differentiation, and we're going to differentiate both sides with respect to x. You can see why implicit differentiation is so useful. So this guy on the left is going to give us dy dx. What happens when we differentiate tangent? We're going to get secant squared y. Okay, and this guy is going to give us 1. Cool. So dy dx is equals to 1 over secant squared y. Okay, this is great and all, but unfortunately, this doesn't really help us much because we don't know. We would rather have it in terms of x. So you could be thinking, what if I just take this and just, plop it in here, and then I'll get secant squared arc tangent x. But then this is also very messy because everything is in some kind of trigonometric function. So there's actually a much better way to represent this in terms of just x, and I'm going to show you how to do that. So first off, we're going to have to look at this guy right here. Hello? So this tells you that if you were to draw a right angle triangle like this with some angle y, the ratio of the opposite to the adjacent length is going to be x, which means one possible combination could be x over 1. There are also other combinations like 2x over 2 or something over something, but I'm just gonna take the simplest form, which is x over 1. So this tells us that the hypotenuse must be 1 plus x squared because Pythagoras, right? So what is the secant squared y? Secant squared y is 1 over cos squared y. So this actually gives us cos squared y, like so. So what is cos y if we were to use this right angle triangle? We're going to get 1 over square root of 1 plus x squared. So we can actually use that and chuck that in here, which is going to give us 1 over 1 plus x squared, because the square root gets squared, it disappears. Therefore, we know that when we differentiate arc tangent x, we actually get 1 over 1 plus x squared. So this is very important. There we go. This is one of the things that you should remember. This is actually part of your new syllabus. So you won't actually see this in the past years before 2020. But past years from 2020 onwards, you would actually see questions like that. So this is something that, yeah, you can't really get much practice in the past years because it's new to the syllabus. But I have prepared a separate worksheet which I will share with you guys on Google Classroom that you can give a go at. Anyway, what happens if we are trying to differentiate arctangent, but instead of x, we have some function of x? Oh no, what do we do? Well, using the chain rule and the 5 basic rules that we have derived much earlier last class, you would actually see that if you work this out, you would get f prime x 1 over 1 plus bracket fx bracket squared. You would get something like this. Okay. Now, let me just show you another example. Let's say the question wants you to differentiate arc tangent x squared minus 5x. Okay, what you're going to get is you start by differentiating this guy here, which will give you 2x minus 5, and you get 1 over 1 plus bracket x squared minus 5x squared. And done. There's actually a bit more to it than that, but we'll save that for integration. Okay, that's it. So technically, in the syllabus, the only thing that they've mentioned is the arctangent of x. But I think it's better if you also know how to differentiate arc cos and arc sine, because, you know, sometimes they might ask you something that is not explicitly written in the syllabus, yet it's implied to be in the syllabus. So let's say they give you y equals to arc cos x, right? And you want to differentiate this. What do? You start by moving cos to the other side. And then you can draw the triangle again. So adjacent of hypotenuse, the ratio must be x. So this should be x. This should be 1, which means this guy here should be 1 minus x squared. Okay? And then we're going to differentiate both sides implicitly. So that's going to give me dy dx. So what happens when we differentiate cos? Well, it's going to give us a negative sine y. So dy dx is actually negative 1 over sine y. And what is sine y? Well, based on your little triangle that you've drawn, sine y is opposite over hypotenuse, which means it's 1 minus x squared. So taking that, chucking this into this, we're going to get negative 1 over square root of 1 minus x squared. And that is that. You can do the same thing for sine, but let me just show you let me just show you here in case you have any doubts. So first we're going to move arc sine over. We get sine y equals to x. Differentiate both sides implicitly is going to give us dy dx cos y equals to 1. Drawing the triangle, it's going to give us x over 1, which means this guy is 1 minus x squared. So dy dx must be 1 over cos y. So cos y based on this little triangle is going to be 1 minus x squared. So we can take that, chuck that in here, we get 1 over square root of 1 minus x squared. And done. So the only difference between this one and this one is that this derivative has a negative. This one does not. Okay? There you go. All right. Having said that, we are pretty much done for implicit differentiation. So all that's left is parametric differentiation, which is actually quite a short topic. But I don't think I want to go into that here because then I think it might be a bit too confusing since you're learning too many new things at once. So I think we'll stop here for today and I'll let you carry on with the exercises, which would be, well, quite a bit since we're doing this one as well. I'll upload the exercises for the inverse trigonometric functions on Google Classroom. And then next class, we will do parametric differentiation. And if you have anything you want to ask for implicit differentiation, next class will be the perfect time to ask, including anything from differentiation, really. So just send me questions and we'll discuss them next class. Otherwise, it will be a very short class because parametric differentiation is a very tiny subsection of the chapter. And ideally, I don't want to start integration yet. I want to make sure that you guys are completely comfortable with differentiation first before we move on to integration, because that is a whole new can of worms that, yeah, if you're not good at differentiation, that's going to be a challenge. So yeah, we're going to stop here for today. Okay, I will send you guys the exercise for 4D and the inverse trigo functions. And I will see you guys tomorrow morning for maths. Okay, bye-bye. Unless you guys have any last minute questions you want to ask. Otherwise, I'll see you tomorrow. Okay, see you guys then. Bye-bye.